Hello, my name is Kyle Smith, and this will be my final presentation for Physics 2. All right, so here are 10 principles that we're supposed to hit. I'm going to do that through just demonstrating, you know, topic and also going in my notebook and choosing some problems that I found interesting throughout the year that I think I should include. Again, how is electricity generated and delivered? So the main idea is Faraday's law. So the change in magnetic flux is going to be our EMF, and so we can use that to pretty much transform the mechanical energy that we generated in these power plants and bring it to the house. All right, so how does Faraday's law work in application? So in most cases, they use a rotating generator. This is a super simple example, but it does it well. It has an angular frequency rotating around a uniform magnetic field. And so basically, what it does is when it rotates around the magnetic field, it creates an EMF, and that is, our electricity. And so we define flux as B times A times the cosine of our angular frequency times time, and then taking a derivative of that, plugging that into Faraday's law, we get what our EMF is, B times A times our angular frequency times our sine of angular frequency times time. And so this sinusoidal curve maps out what the AC current is. So I'd like to note one thing from the previous slide. So what can generate that magnetic flux is a change in area, a change in orientation, or a change in the magnetic field. And that's actually seen in one of our problems, problem 9.2, where we had to find current. And what drove the magnetic flux was the changing magnetic field. And so you just did the typical steps and then did like Ohm's law to solve. Anyways, so we have this transformer here. And so what a transformer does is that it can either step up our power or step down our power to get, what we need from it. And so when we're transporting it across long power cables, I'll get into that next slide, we need to step up our voltage. And if we're bringing it to a house, obviously we don't want like a 10,000 volt outlet. That would be horrible. So we need to step it down. So transformers are used. And so it's governed by mainly by this equation. Um, the voltage of our secondary over the primary is equal to the ratio of our turns, pretty much. And it's just a super simple, honestly, not that complex way of manipulating voltage, right? I'll quickly get into why power lines have such high voltage. So power loss is determined by P equals I squared times R. So you can see here that a big current is not very advantageous because that will crank up our power loss by a lot. I also know that power is equal to V times I, so V is inversely proportional to I. Therefore, if we have a higher V, we have a lower I. So therefore, just make the V as ridiculously high as possible, lower I as much as possible. It's going to be the same power because P equals VI and it will be good. So for this first topic, it's pretty wide in breadth. So it goes over magnetic fields, Faraday's law, AC circuits, transformers, energy conversion, and real-world engineering. Yeah, and so some real-world examples of this Faraday's law and how electricity is brought to our homes. We could generate it through wind, hydro, chemical. It doesn't matter. Uh, well, it does for climate change, but for our purposes, we just need the mechanical energy to get generated into electrical engineer energy. And one good example of a grid system still being built is an EV station. Obviously, it needs a lot of work still. Um, like the goal would be to get EV charging stations at every gas station, but we're getting there. Next topic is Maxwell's equations and the speed of light. For this class, I thought it'd be good to give Maxwell a shout out because without him, this stuff wouldn't really be a thing or just be called something different. I'm sure someone along the way would figure it out, but um, he figured out how to connect magnetism and electricity and make it one comprehensive kind of thing that is very, very interconnected. So from those four main equations, the bottom two were Faraday's law and Ampere-Maxwell's law. And so basically, those two kind of tell us that a changing electricity field creates a magnetic field. That's the Ampere Maxwell, and then a changing magnetic field creates an electric field. That's Faraday, and yeah, those equations govern how our waves form and why they work the way they do. So wave speed is calculated a couple of different ways. Maxwell predicted that the speed of light is 1 over the square root of the permeability times the permittivity of free space. There's also a couple of other different ways of doing it, like the magnetic field or the electric field divided by the magnetic field, and then frequency times wavelength. And so I wanted to go over a practice problem that was Unit 12 that went over a lot of conceptually different things across this semester that also used the speed of light and this ratio to show. So it was a satellite that was 575 kilometers above the Earth's surface, and it generated a uniform electromagnetic uh, wave at 92.4 megahertz uniformly in all directions, and it gave a power rating of 25 kilowatt. And so we were supposed to find the intensity at the Earth's surface, our electric field or magnetic field, and the force on the panel. Um, and so the plan was intensity is power over area. And since we are given a uniform um, electromagnetic field, and it spreads out in a sphere with the center being a satellite. And so here, I equals P over 4 pi r squared because our area, since it's spreading out uniformly, is a sphere. And we plug in the appropriate r. Um, we want E naught and B naught, and they are related by the speed of light calculation. E naught over B naught equals C. Uh, and so we can find E naught from intensity. And so intensity is 1/2 times our speed of light times our permittivity of free space times our electric field squared. And so rearranging E naught equals 2 times intensity over speed of light times permittivity, and take a square root of that. And to find B naught, it's just related by C and E naught. And then to find the force is just pressure times area. And then just rearrange from the speed of light, we're also given another relation, intensity over pressure. It's also another way of calculating speed of light. And so pressure equals intensity over speed, and then force equals pressure times area, and then it would just be uh, I over C times A. And yeah, that's the workflow for that problem, but I thought it was a good example. It demonstrated, a lot of different aspects. Shown is our electromagnetic spectrum. So it starts at radio waves, and we go up from there to microwaves, infrared, visible, ultraviolet, X-rays, and gamma rays. So you can see the visible spectrum is just a really, really tiny, tiny bit of the whole electromagnetic spectrum. And so they're all just the same frequency or the same phenomenon, just altering in frequency. Radio waves have a much, much lower frequency than, let's say, gamma ray. So as you move right, wavelengths goes down, and our frequency and energy go up. Demonstrating this topic is how electric fields and magnetic fields relate, the calculus behind that relation, the properties of the waves, and then the foundations of modern communications. There's a lot of technologies that are applicable for this topic. Anything that involves the electromagnetic spectrum is going to be included, um, such as Wi-Fi routers or radios, or even like medical technology. Um, but yeah, anything related to magnetic fields, that relation with electric fields, that's going to be applicable for this topic. So moving on, here I'm going to work out an example of a Gauss's law for a uniformly charged sphere with two cases, one inside the sphere and one outside the sphere. We'll see how the math changes a little bit on that, but it's more so to demonstrate, I think it was like section 1 and the 10 learning objectives. All right, so we start with Gauss's law. And so that we're just considering a arbitrary sphere, uh, given an arbitrary field. So everything is hypothetical. So we start with Gauss's law, and it's the line integral of E dot dA equals the charge enclosed divided by the permittivity. Because of our spherical symmetry, our electric field points radially and is uniformly distributed. So our integral simplifies to E times 4 pi r squared, area of the sphere, and then equals Q enclosed divided by E naught. So outside the sphere, we just treat R as big R. And so all our charge is enclosed, the whole thing. And so we just rearrange and solve for E. And this behaves exactly like a point charge. So it's a very nice simplification when you approach these problems. And inside the sphere, it's a little bit more dicey. We have to include a density constant rho, and then now we take the Gaussian sphere of radius r inside that larger sphere. And so our volume is just going to be 4/3 pi r squared of our Gaussian sphere. So our enclosed charge is density times volume equals um, rho times our volume. So we do that math, and it's Q, and then it's a ratio of our radiuses, pretty much our Gaussian sphere versus our actual sphere. And so we apply Gauss's law, and then we sub in what that Q is. And rearranging, we see that it creates a linear proportionality um, between E and R. So as R gets bigger, E gets bigger as well. And we see that with this graph. We see that it starts at 0. We see that it peaks right here. That would be at R equals R. And then it goes down from there at a 1 over R squared relationship. All right, so now let's bridge the gap to more practical, kind of hands-on. So I want to go from DC to AC and discussing RC, RLC, and resonance. So first, DC, I'd like to go over just an example, I think, that demonstrates this well. So we have an electric eel that's 140 rows of plaques. They have these electric plaques that generate electricity. Um, and each row contains 5,000 plaques. And so each plaque has a voltage of 0.15 volts and a resistance of 0.25 ohms. And the surrounding water has a resistance of 800 ohms. And it's asking us about the current. And so most of these DC problems simplify to just manipulating V equals IR in some sort of way. And so here it's just I equals V over R. And so we need to find the V net of our problem and our R total. And so our V net here, because because each plaque is in a series with each other and in the row, the voltage gets shared among them. So we just multiply our 5,000 total plaques times the voltage of 0.15. And so at each voltage we add it. And so it's in total 750 volts. And so there's 140 rows in parallel. They're going to share that 750 volts across each row. All right. So now we know our the V net for this problem. So now we just need the R total. So each plaque is 0.25 ohms. So in series, we see here that we just add each resistance. So 0.25 times 5,000 is 1,250 ohms. But here, so that's the resistance of just one row, but there's 140 rows. And since it's set up like one row after the other, that's going to be in parallel. And so we use the resistance rules for parallel. We do 1 over 1,250, and we add that 140 times because there's 140 rows. And you see it's 1 over, so we have to flip it over, and it's going to be 1,250 over 140, and that was going to be our resistance. And so I equals 750 over 888. And so this problem, I think, demonstrated um, just kind of how DC circuits work and how you kind of got to think about them with the resistance. So there was a couple problems where it involved RC charging circuits this semester. I thought I had to mention it. But basically, this equation governs how our capacitor charges. And so using this, we can figure out, like after a given amount of time, what the charge is. Um, but so a capacitor, the way its equivalent capacitance works is it is if it's in a series, then it's like a resistor in parallel where it's 1 over R, so it's 1 over C. And if it's in parallel, then it's like a resistor in series where we just add them. So that's the general rule to how it works. So now it's time to transition to AC circuits. So instead of it just being a direct power supply, it's an alternating power supply governed by that sinusoidal curve we mentioned earlier. And that was from Faraday's law on the magnetic flux. But it changes sinusoidally, and then capacitors and inductors oppose the change in current. So I thought for a series RLC circuit that just doing a practice problem would be the clearest. All right, so we have a RLC circuit driven by AC source. This is practice problem 11.1. Here we have resistance R, inductance L, capacitance C that opposes the current in a different way. And the problem wanted us to find impedance, the current amplitude, and the phase angle. Uh, and so my plan was to find the reactance of our inductor, reactance of our capacitor, find our net reactance, angular frequency by 2 pi f. And so our impedance comes from that formula. And then assuming a sinusoidal source, our current is I naught times the cosine, and then our amplitude is based on that sinusoidal source. And then the peak amplitude is V naught over Z, and then that phase shift can be found through tan phi equals the net reactance divided by our our uh, resistivity. Um, so yeah, it was just this problem was a good showing of how instead of it just being V equals IR, it's V equals IZ, and then uh, with it being two different sources of reactance, there comes a phase situation. At resonance, our reactance from our inductor and reactance from our capacity is equal. So let's just plug that in. If XL equals XC, then our impedance is just R. Uh, and then looking at the frequency calculation, um, the resonance frequency is equal to 1 over 2 pi times the square root of our inductance times our capacitance. The key takeaway here is that from resonance, our current is maximum. And that's kind of all we want to figure out. That's when our graph is like at its peak. So here's some real world applications of RLC circuits. The best one being audio tuning because you can switch the inductance of our capacitor and that will affect our net inductance will affect our voltage and it's a nice way of figuring it out. So here's a full demonstration of topic 4. It's pretty wide in breadth, but DC circuits, Ohm's law, RC time constants, capacitors, inductors, AC impedance, resonance, and applied electronics. So for topic 5, I want to just mainly discuss um, what rays are and how they differ from light waves themselves. And so uh, here's kind of just the general how light rays work, and these are the formulas we use to explain all of it. But the key idea is that light behaves like rays when the wavelength is much smaller than the object it interacts with. U is the object distance and V is the focal distance, where F is the focal length. So there's 3 standard rays, parallel, focal, and central. Where the rays intersect is where the image is formed. A real image is where the rays meet, so you can catch it on the screen. We see that with the concave mirror that it intersected right where the image is shown up where the person can see it. But with a virtual image, it's a projection of the image coming back, so it's not actually it. Um, so object beyond the focal length rays converge in front of the lens in the mirror that gives a real inverted image, and then objects inside the focal length and the backwards extension meets, which gives the virtual upright image. Here are the optical instruments, just some common examples of how we can use lenses to manipulate light so that we can see stuff clear, closer up, stuff like that. A big part of this class was using this double slit interference experiment to show that light was a wave. And the main implication was that from it, we saw a constructive and destructive interference pattern, which is only possible if such thing was a wave. Therefore, light is a wave as well. So for diffraction and resolution, when light goes through small openings, it spreads out in all directions. This concept is why there is a limited resolution. So as it goes further on, the intensity decreases. A smaller aperture means a worse resolution, whereas a smaller wavelength means a bigger resolution. And this graph is the intensity graph. We did something similar in lab, and we had that n values where we had to calculate it out. It was a really cool lab. But here's a nice comparison between rays and waves. So for rays, light is a straight line ray, a nice simplification for lenses, mirrors, and imaging. And we don't consider any wave property when we assume a ray structure. So not assuming that wave property simplifies things a lot. And then for waves, light are waves, demonstrated through double split, which explains why there was interference and diffraction in the experiment. And so when a wavelength is much smaller than the system size, we just usually use the optics, the light rays, and the formulas from that. So yeah, this demonstrated geometrical optics, wave optics, the physical meaning of wavelength, and real-world imaging systems. This is the last slide, but uh, I think I hit all the topics that I wanted to hit on, and I went into as much detail as I could for about 20 minutes for this class. This class was a lot. And so I guess let me propose my grade. So I propose that I make a B in this class. Um, I didn't get to do all the quizzes. I know to propose an A, you'd have to do 13 out of 14. I only did 11. Um, and I feel like I definitely demonstrated all the learning objectives, but in terms of the requirements, I didn't hit it. So that's why I'm saying I get a B. But yeah, I appreciate this class. It was cool learning about light and just how important this class is for uh, technology and life itself. Because before this class, I was like, what's the point? Like it's just circuits. It's so specific, but literally everything we use has circuits in it. And so pretty much, if you know this class, you know the world. Cool. But but yeah. So yeah, this is my final presentation. Thank you.